It's great to be here. I thought to start out I would make a comment. I understand, or I even know, that a great deal of the forefront of cold atom and cold molecule physics is the possibility of simulating the response of much more complex quantum systems through these cold atoms, through arrangements of cold atoms, how they interact, and so on. And I think this is particularly important, or I understand it's particularly important in solid-state physics. So I'm going to talk about what might be considered an analog in attoseconds and high harmonic physics, about the connection between atoms and solids, and what we might learn about solids, and how we can use solids to control the production of attosecond high harmonic pulses. So maybe to start with, I would like to make another comment, and that is that we, in laser physics, have learned to control light at an awesome level. You also, in cold atom, and especially in precision measurements, have done so in the Fourier transform domain. We've learned to control it at an awesome level. It's possible now to exert forces on electrons or any charged particle that exceed or equal the forces they see from their constituents of matter, to apply them on a time scale of valence electron responses, and thereby have light share with the rest of the material responsibility for the electrons and the spectrum. In other words, light can take partial control over the electron motion. And the place where this is most easily applied and most beautifully applied is in recollision physics. You might say in recollision physics, there is a place right at the border when the electron is bound or not bound, where this tug of war between the laser field and the ion takes place, and the laser plays a major role. If the electron leaves the barrier, leaves the tunnel, afterwards, 1 over r squared means the force of the ion retreats, but the force of the laser field remains. And so the laser field dominates through all of the rest of the motion of the electron over one cycle, and that motion, in the presence of a strong infrared field, moves the electrons around tens of angstroms, depending on the wavelength of the light. The fields that are involved are somewhere on the order of 3 to 10 volts per angstrom, and so the electron can pick up energies on the order of tens of EVs, hundreds of EVs, or if the mid-infrared driver, even up to kilovolts. The image here shows you a classical electron and how it evolves in that field. It moves away, carried by its momentum, it moves uphill, and then driven by the reverse of the laser field, it comes back and recollides the ion from which it left, where it can do one of 3 things. It can inelastically scatter, it can elastically scatter, or it can recombine, giving off a photon. F equals ma tells you that the electrons have a moment of birth, a moment of recollision, and an energy. So there's a mapping of moment of birth to energy and time of recollision. And it's illustrated here in a qualitative sense. The photon energy from this recombination scales from red to green to blue, and the numbers I put in are completely arbitrary at this point. They depend upon the intensity of the field and the wavelength. If this process is repeated cycle to cycle, then we get a series of attosecond pulses, because this is approximately 1 attosecond time scale. We have a series of attosecond pulses, and those are harmonics, and these are the high harmonics that you see. In this case, stretching from about the 17th harmonic, about 20 few EV, all the way up to about 60 EV, but with an infrared driver, it can stretch up to a kilovolt. So this is high harmonics. If there's only one time of recollision, one mapping, then this is the attosecond pulse that is in the title of the talk. Such an attosecond pulse is created chirped, red to green to blue, but with dispersive materials, the chirp can be removed, and that's what takes us to the current state of the art, which is 50 attoseconds. So this is a classical perspective on a quantum mechanical problem. It was a discussion last night for those of you who were in the audience last night in the discussion point. But you can have a quantum mechanical perspective, and I want to go to that next so that you understand that before we move to solids. So the classical electron, of course, is a wave function. An electron does not ionize by classically going over the barrier, but it must tunnel, or quantum mechanically go over the barrier, but let's say tunnel, through the barrier, creating a wave packet in the continuum. That wave packet is pulled by the laser field and stretched and distorted, and I represent the electron wave packet by this motion out here, which is sort of a classical-like motion. And when the electron wave packet is brought back to the ion, it overlaps the wave function from which it left. Overlapping the wave function from which it left causes a dipole, and that dipole allows for the transition of the electron down to the ground state, giving you radiation. And so attosecond pulse production from a quantum mechanical perspective is really a quantum antenna or an electron interferometer. Really an electron interferometer. Each piece of this can be relatively easily understood in a quantum mechanical sense. And the electron gains hundreds or thousands of radians of phase along this trajectory. The link between quantum mechanics and classical is semi-classically regions of birth lead to components of the wave packet coming back at regions of time and with an energy over a region of a blur of energy space. And so a classical trajectory maps onto a quantum trajectory in that way. I just repeat the figure once more to say a little bit more about this. This electron, when it comes back, can have energies on the order of 100 EV, so wavelength in the order of 1 angstrom. It can even have 1,000 EV, so wavelength in the order of a fraction of an angstrom. And when it comes back and it scatters, it can do diffraction, it can give you a holographic image, or it can do tomography on the orbital from which it left. And one of the iconic images from this field is the tomographic image of the highest occupied molecular orbital of nitrogen, taken by looking at only the spectrum created by high harmonics in the way I've told you so far in this talk. So it's as if the molecule or the atom took a picture, took a selfie, took a picture of itself. I put it up there for you to think about it. I wanted to leave this slide in for one other reason. The electron that goes over and forms this interferometer that we've discussed so far can be controlled in just the same way that light in an interferometer can be controlled. We could add easily a second color of light, the second harmonic of the fundamental, and phase it in such a way that as the electron goes along this trajectory, its action is increased. We pull it a little extra, we push it a little extra as it comes back, changing the trajectory, changing the action of the electron along the trajectory. If we were to delay the second harmonic by pi, instead of pulling it along the trajectory, we push back on it as it makes its trajectory, and it's possible to optimally push back and push forward in such a way as to tell what the trajectory that leads to a given color light is. So I want you to keep that in mind. 2 colors. The second color, weak, is like a micrometer in the interferometer, and it allows you to move the phase of the light in this trajectory just a little bit, depending on the relative phase between the fundamental and second harmonic. With this, I'm going to move now to solids. So this is the underlying physics between what happens in gas. All of the rest is the technology of attoseconds and high harmonics, which I will not go through. Let me just leave it by saying during the last 15 years, that's the duration, that's the time we've had attosecond pulses, we've extended the 50-year tradition of ultrafast science. We've reached pulses that are about 2 orders of magnitude lower than what they were previously. Now about 50 attoseconds. What I've told you is a different kind of nonlinear physics. It's a nonlinearity that's not perturbative, like we're used to in normal nonlinear physics. It's a nonlinearity that comes from this strong field approximation, and where you can almost get an intuition from classical physics. Again, a subject that was discussed last night. So we extended the 50-year tradition of nonlinear optics, opening, I think, a whole new direction in nonlinear optics, and you can judge it as we move to solids. And in addition, we extend a 100-year tradition of X-ray science, integrating X-rays and laser physics, thereby extending the reach of lasers to about 2 orders of magnitude into the X-ray region. So it's quite a set of accomplishments. In 2011, in an experiment done in Ohio State, the student that ran the experiment was a postdoc. His name was Shambhu Gamir. Showed high harmonics of 3.5 micron light created in zinc oxide. This was quite a surprise, at least to me, and I think to many people in the community, because somehow it seemed that an electron that went over a trajectory like I showed you and returns and interferes with its initial state would not maintain phase. It would dephase over that time. That was sort of my bias. So I want to start out by rediscussing how you think about this in solid state language, what I told you before. So an electron that is freed from the atom moves on a parabolic band. This is momentum versus the energy, and that's the electron. The ion that's left behind is equally charged. It also moves in k space, so it moves in momentum space, but because its mass is so large, it's essentially a flat line in momentum space. When we ionize, we create an electron essentially at rest from the ion, and both the electron and ion then move in momentum space, move and go through trajectories like I told you before. However, the electron and ion, if they find each other, can recombine, creating a photon, and the photon would be like a band-to-band transition in momentum space at some region of energy and some momentum. So if we measure an electron or photon of this energy, we know in this band-like picture it made a band-to-band transition if we have recollision-like harmonics. That is, that 2 bands are important for the creation of the harmonic radiation. There is another mechanism in gases. In Ottawa, we call it Brinell harmonics, and to my knowledge, he's the first one to have looked at it, but I could be wrong about that. So we call it Brinell harmonics. And it's easy to see as well, and it plays a deep role in solid-state physics. So let me just mention it. When you create an electron from an atom, you create something that will give you a current, and the current you create is going to be the charge of the electron Q, or E in this case, the number of electrons times the velocity of the electrons. The charge is not so interesting. The number of electrons tends to go up in a stepwise behavior because ionization in these cases is tunneling, and tunneling occurs near the peak of the field. And so the electrons has step-like behavior here, and the electron oscillates in the laser field in a sine omega t, which is not so interesting. However, Fourier transformed this, and the step-like behavior leads to a series of harmonics. Not so interesting in gases because these are low-level harmonics. They're 3, 5, 7 maybe, and they don't lead to high harmonics. And so largely it's ignored in gases, but in solids the band will have a more complex structure, and so the velocity of the electron in the band is more complex, and therefore it can contribute significantly to the highest harmonics as well. We set up, I shouldn't say we, Thomas Brabant's group, me working with them, but they're the theorists in this, set up a 2-band model to look at zinc oxide. Look at zinc oxide as carefully as we can, and the results are shown here. The spectral intensity in arbitrary units is shown on the right-hand side. You might notice that the units are 4 orders of magnitude, and so although the harmonics, which you see here distinctly, look kind of small, they're really quite large, quite distinct from the background. And you see 2 colors of curves. I want you to concentrate on the lower one where we've added dephasing. The upper one has no dephasing in the model, so the lower one is more important. And so there are 2 curves, and these 2 curves encode the 2 different sources of harmonics. the two-band source, where the electron goes from the conduction to the valence band in order to give you the photon, and the one-band source, where the electron moves on the conduction band in this complicated way that's analogous to the Brinell harmonics. And so it was quite a surprise to us in Ottawa, as we did this model, to find that the harmonics are dominant from the two-band source, or the recollision harmonics, dominant by 4 to 6 orders of magnitude according to the model. In fact, we were so surprised that we went to a lot of trouble to try to improve our potential energy curves and things like that, but it never went away. The model predicts something very similar to what I described to you before, that the red photons, the lowest energy photons, are created first, that the greener photons, the higher energy photons, are created second, and the most short wavelength photons are created finally. And so that's what the model prediction is. This is a windowed Fourier transform, the colors in the background of what the emission is given by. And the white curve is a classical-like simulation of the electron on the bands where the electron has the band-corrected mass. So it seems from the model that recollision plays a role. So we set up an experiment, an interferometry experiment, much like what I described to you in the early case. Let me go through it again. Let's imagine an electron is created, and we can organize the phase in such a way that we add a little bit of phase to the trajectory, or subtract a little bit of phase to the trajectory. From the second harmonic, the trajectory generated by the fundamental. In this case, we see it subtracting. The blue is the new curve. We see it subtracting, and so half a cycle later or earlier, it added to the phase, breaking the symmetry, leading to even harmonics in the zinc oxide cut that we have is a completely symmetric cut. And so in this figure here, where we look at this experimentally, we plot the delay between the fundamental and the second harmonic. That's the critical issue. And we plot the even and the odd harmonics here on the same curve. Both are normalized to their maximum value, and these numbers give you the ratio between the even and odd harmonics up and top. The referee wanted them all on the same scale. What we look for is a phase delay between the fundamental and second harmonic that scales with the frequency of the light, the harmonics that are created, and you see just such a phase delay right there. And that's the experimental result. And we can fit the experiment to the predictions I said to you earlier, and you see that the fit is very good. The single band contribution is down here, and it does not fit. There are a number of things to see from this. This spectrum is rather limited. It only goes up to 18 harmonics of zinc oxide, yet the pulse that we create from an infrared driver is 1.7 femtoseconds in duration, or the typical pulse within the train of pulses. The intensity we use is 10 to the 12 watts per square centimeter, but the intensity of the second harmonic is 10 to the 5 orders magnitude less. We are truly perturbing the trajectory of the electron by the second harmonic pulse. Okay, so this confirms in zinc oxide. We've also looked at silicon, and it behaves very similar to what I've shown you here. And I think it's largely accepted that in the traditional semiconductors, recollision, just as we have in gases, plays the fundamental role, and the block oscillation term, which is often called in solids, or the Brinell harmonics, are less important in the traditional semiconductors that we're used to thinking about. And large bandgap semiconductors, I'll show you at the end of my talk, if I have time, that this is not the case. So what can we do in solids with this new ability? Well, one of the things I showed you when I started out was it's possible to image an orbital of a molecular system by this interferometric-like technique. Specifically, it's a tomography technique that we use. So can we do something analogous in solids? The first thing to maybe think about is, can we get the band structure of the solid just optically? It should not be out of the question, because we create an electron by making a jump across the band. We move the electron under the influence of the laser field one way or the other. The electron and hole find each other, they recombine, and they give off radiation that tells you about the band differential between one and the other. So maybe it's possible we have the energy from this if only we know the K vector. In fact, a two-color experiment, just like I showed you before, gives you two knobs, the relative phase between the fundamental and the second harmonic, as well as the frequency that we observe coming out. And those two knobs allow us to uniquely determine the band structure. This is a simulation of what we would see in zinc oxide. We simulate because it allows us to go right up to the band edges, the greatest band differential. I've only have 5 minutes. I'm going very much slower than I thought. But is that true? Because it's only 20 after 9. Well, that is true here. Maybe I misunderstood the time I have. I'm going to have to jump. Okay, so this is the band structure that we get from reconstructing, and the band structure of the original band is there in red, and you can see that we get the band quite accurately. So what do solids offer us in the high harmonic community that you do not have from gases? So they offer us passive and active structures. So I'm going to have to go through this rather quickly because I somehow have lost 5 minutes. 2-micron radiation, irradiating a sample from the back, which has a set of pyramids as shown here. The radiation diffracts from the pyramid, or is created in the pyramid structure, and we can go to the Fourier plane and look at the diffracted beam, showing that the radiation from all of these pyramids is coherent. We've structured the radiation so it goes into the pyramids, increases at the apex, and we see the diffracted pulse here. And if you're good and you got good eyes, you can see them in real color because this is a real color image taken here of the harmonics. And of course, we can re-image that onto a CCD camera, and we see that the radiation comes from exactly those regions where the radiation is peak. So not only can we structure the surface by putting pyramids on the surface or restructuring the surface morphology, we can also place gold nano antennas on the surface and control the radiation from the nano antennas. I'll skip this part. Furthermore, we can add or change the chemical composition by injecting particles and changing the phase and amplitude of the radiation. This is a zinc oxide sample in which we inject gallium atoms in a zone plate-like pattern. The smallest zone is 2.5 microns in diameter. The zone plate pattern allows us to look at the structure of the beam anywhere from the surface using conventional optics, from the surface all the way out to the maximum focus of the zone plate. And we see that the focal spot diameter is exactly what you expect. In other words, we create radiation that has the curvature on it already by its creation, the curvature that allows us to go to the... so we create focused radiation in the process. And I think this is important for the future, for future focusing of high harmonics. I'm going to skip, well, I have to skip almost everything from now on. I told you I want to say it in words, although I have a movie here to show it. I showed you that we can create harmonics, and we can perturb those harmonics with 10 to the minus 5 less than the field that required to create them. The field that breaks the symmetry in this case, 10 to the minus 5, is only a few volts per micron. And so these are fields that are on the scale of those that are in conventional electronic devices. And so it's possible to go into electronic devices, put voltages on electrodes, and see those voltages and record them in the even harmonics that are created. So I have a movie here, but I will skip that. Finally, and I'm only going to say this then in passing, because again, I'm in trouble with time. I'm going to say this in passing. It's possible to integrate solids and gases into a single experiment, especially if we use large band gap solids such as quartz. we can use the large bandgap solid as a source of harmonics itself, or as a way to use the chi-3 characteristics to reshape the fundamental beam. In this image, I show a beam being reshaped, a few cycle pulse created outside, being reshaped by self-phase modulation at intensity of 3 times 10 to the 13 watts per square centimeter in a 90 micron thick crystal, being reshaped, and the crystal being crystalline quartz produces second harmonics simultaneously. So we have 2 ways of creating the same color, and we can use them just like you do in frequency comb measurements to stabilize the phase and restructure a pulse, and that's how we make the pulse I showed you to begin with. There's no reason why that can't be followed by xenon or by another piece of quartz, and there's no reason why we cannot measure the characteristics of such pulses. So in conclusion, there are opportunities everywhere in solids, I think just like there are for cold atom physics. It's to apply nonlinear optics to electronics. I said it, but I didn't show you. To measure rapidly changing band structure during laser damage, laser machining, or under high pressure materials. I did show you that we can do that. To study the structure of liquids, the harmonics they create. It's already just beginning in experiments now. To image dopants that are used to control harmonic amplitude and phase, and to use them to control, I've shown you that that's possible. I've shown you it's possible to solve the focusing problems for soft X-rays. It should be possible to measure dephasing because the recollision harmonics are so sensitive to phase. It should be possible to image orbitals of deeply bonded excitons, to transfer attosecond technology to solids, and to probe 2D materials, which are so interesting now, and so I wanted to just end up by showing you harmonics of graphite, and therefore real-time surface chemistry, because a single monolayer can produce radiation through this high harmonic process that is observable and measurable. Thank you very much. And this is the group.